Hi and welcome to the last part of our discussion about compaction. So, previously, we have discussed all the chapter contents, and in this video, we'll try to solve some example problems regarding those topics under soil compaction. So for the first problem, it says that a soil is compacted in a cylindrical mold with a volume of 1,000 cubic centimeters at 6 different water contents. So using the same compactive effort, that is the test 1. And for another test, so after the test 1, the samples were extruded and weighed, and then another test, which is test 2, was performed but with a larger compacted effort. So the water contents and the wet masses of the samples from the two tests are given in the table. So we are asked to solve for the dry densities and the optimum moisture content for each test. So we can use the formula rho dry, or the dry density, is equal to the wet mass all over the volume times 1 plus the moisture content. And then, so you will have to simply substitute the wet masses, and then the volume is equal to 1,000 cubic centimeters. And then for the moisture content, so you have to substitute this up to this one with the corresponding wet mass and the water content. And so after that, you will get that these are the dry densities for each test and for each corresponding water content. And then, so this is the first part of the question. And then the second part is we have to determine the optimum moisture content. So if you are going to plot the calculated dry densities, you will arrive with this graph. So you can see that for the first test, which is the blue, so our optimum moisture content for test 1 is equal to 17%. While for the second test, the optimum moisture content is equal to 15. So you will notice that for the second test, a larger compaction effort was used. So you will arrive with a smaller optimum moisture content, a larger dry density. So, because we have previously discussed that the um, compaction effort is one of the factors that affects the compaction of the soil. So again, a larger compaction effort means lower optimum moisture content and then higher maximum dry density. So, for the second problem, a standard Proctor test was carried out on a clayey sand and the compaction curve is shown in the figure. So, the specific gravity of the soil grain is 2.71 and we are asked to determine the maximum dry density, the optimum moisture content, the void ratio at the optimum moisture content, and the degree of saturation at the optimum moisture content. So, for the maximum dry density, we will simply refer to the figure, this one, and we can write that the maximum dry density is equal to 1.97 tons per cubic meter. And then, for the optimum moisture content, again, we will simply refer to the figure. So, the optimum moisture content is equal to 11.50%. So, as for the void ratio, at the optimum moisture content, we have to conduct some calculations. So, now that we know the maximum dry density, so this is 1.97 and this is equal to 2.71. So because this is the specific gravity, and then for the density of water, so that is 1 ton per cubic meter. And then this is all over the 1 plus the void ratio E. So the void ratio, so I forgot to write the unit. So this one, the maximum dry density, is in tons per cubic meter as well as the density of water. So this is also tons in cubic meter. As for the specific gravity and the void ratio, they are unitless. So our void ratio is equal to 0.3756. So, for the last part, we are asked to calculate the degree of saturation at the optimum moisture content. So, we'll have to use the formula. The specific gravity times the moisture content is equal to the void ratio times the degree of saturation. So, the specific gravity is known, 2.71 times the moisture content, which is 0.115. This is equal to 0.3756 times the degree of saturation S, and you will arrive with 0.8 8297, or if you want to express this in percent, so this is equal to 82.9739%. So, for the next example problem, we are asked to refer to the previous problem, and some specifications for compaction are presented. So, it states that the compaction specifications require that the relative compaction be at least 98% and the water content be within negative 2% to negative 0.5% from the optimum water content. So, a sand replacement test was carried out on the compacted earthwork where 1,240 cc hole was dug into the ground. So, the mass of the soil removed from the hole was 2,748 grams and later became 2,443 grams after drying. So, does the compaction meet the specification? So in the previous problem, we have determined the maximum dry density and the optimum moisture content. So, in this next problem, we are asked to check whether the soil in the field meets the specifications required. So, we have two. So, first is using the relative compaction, and then the next is the water content of the soil sample. So, by the way, the sand replacement test indicated here is the field density test, which is the sand cone method. So that is another term for the sand cone method. And then so first let's check the relative compaction. So before we can check the relative compaction, we have to calculate the actual compaction in the field. So we have to compute gamma D is equal to 2443. So we are using the dry grams all over the volume of the hole, which is 1 to 40 cc. So this is equal to 1.97. And we can express this as grams per cubic centimeter or tons per cubic meter. So this is just if you will try to convert, this two will only equal. And let us check the relative compaction. So in the field, in the laboratory, we have determined that the gamma D max is equal to 1.97, and 98% of 1.97 is equal to 1.93. So 93. So since our field dry density, not unit weight. So density. So our dry density in the field is greater than 1.93. So we are okay with the relative compaction. And then let us check from the optimum moisture content. So it states that the water content be within negative 2% to negative 0.5%. So, and our optimum moisture content in the laboratory is equal to 11.50%. That means we have to subtract 2. So, this should be in between 9.50% to 11%. So this should be the range of our moisture content. So now let us calculate the actual moisture content. So the moisture content is equal to 2748 grams minus 2443 grams all over 2443 grams. So, calculating, we have I will multiply this by 100. We will get 12.4846%, which is greater than the specified. So therefore the soil meets the specification for the relative compaction, but not in the moisture content. So since our calculated moisture content is greater than the specified, we can say that it is wet off optimum. So for the next example problem, a laboratory compaction test for a clayey silt are given in this table. So we have the moisture content and then the dry unit weight. And so for another, following are the results of a field unit weight determination test performed in the same soil by means of the sand cone method. So we have the data listed here, and then we are asked to determine the dry unit weight of compaction in the field. So let's follow the steps. So part A. So for our mass 1, we have the weight. So in this case, we are dealing in terms of mass. So we have the mass of the sand plus the jar and the cone before use. So this is equal to 7.59 kilograms. For M sub 2, this is the mass of the wet soil excavated from the hole. So this is equal to 3.007 kilograms. And then for the M sub 3, we have the weight of the dry soil, so we can calculate that using the formula. So 3.07 kg all over 1 plus the moisture content of the soil. So that is 10.2%, so 0.102. And then the weight of the dry soil is now equal to 2.7287 kilograms. And then for the M sub 4, that is the weight of the sand, the jar, and the cone after filling the hole. So this is equal to 4.78 kilograms. And then for M sub 5, we have the weight of the sand to fill the cone and the hole. So we can get this using M sub 1 minus M sub 1 minus M sub 4. So this is equal to 7.59 minus 4.78, and this is equal to 2.81 kilograms. So now that we know the weight of the sand to fill the cone and the hole, and we can now calculate the volume of the hole. So this is equal to 2.81 minus the mass of sand to fill the cone. So that is equal to 0.545 kg all over the dry density of the sand. So the volume of the test hole is equal to 1.4427 times 10 raised to negative 3 cubic meter. So we already have the dry weight of the soil from the hole, and we already know the volume of the hole. So we can now calculate the dry density of the soil in the field. So this is equal to 2.7287 kilograms all over 1.4427 times 10 raised to negative 3 cubic meter. So this is equal to 1,891.3842 kilograms per cubic meter. But the question asks for the dry unit weight, so we have to multiply this to the acceleration due to gravity, G. So, rho V times G. So, this is equal to 9.81 meter per second squared. So, we can get 1/8 and so, if you multiply this in kilograms per cubic meter and then meter per second squared, you will arrive with Newton per cubic meter. So, let's divide this by 1,000 to express the dry unit weight in kilonewtons per cubic meter. So, you will get 18.5545 kilonewton per cubic meter. So, this is the dry unit weight of compaction in the field. So, next is we are asked to find the relative compaction in the field. So, the relative compaction is again equal to the dry density in the field, which we have calculated earlier, and the dry maximum density. Or yet, since the dry unit weight and the dry density, the dry unit weight in the field and the dry unit weight of the soil in the maximum dry unit weight of the soil determined in the laboratory is, we can also use that. So, this would be instead. Right. See, since we are talking about unit weights, so we can also determine that. We can also use that to determine the relative compaction. So, we are already given with the results of the standard Proctor test, or the laboratory compaction test rather. So, it is not indicated if the test was the standard Proctor test or the modified Proctor test. So, similarly, we have to just plot the moisture content versus the dry unit weight. You will arrive with this one, and you will notice that the maximum dry unit weight is equal to 19 kilonewton per cubic meter. So, therefore, a relative compaction R is equal to 18.5545 kilonewton per cubic meter all over 19 kilonewton per cubic meter times 100. So, this is equal to 97.6552%. So, this is the relative compaction. So, for the next example problem, so a soil sample was compacted and the result of the standard Proctor test shows that at 100% compaction, the soil weighs 131.10 pounds per cubic foot with the optimum moisture content of 14%. So what is the maximum dry unit weight of the soil at 0 air voids in pounds per cubic foot? The specific gravity of the soil grains is equal to 2.67. So, to determine the maximum dry unit weight, so this is equal to gamma D max. This is equal to GS times the unit weight of water all over 1 plus E. But we are looking for this one, and then this is known. We know the value of this one, but we do not know the value of the void ratio E. So, we'll go to the formula. Specific gravity times moisture content is equal to the void ratio times the degree of saturation. So, remember that at 0 air voids, the volume of the voids is equal to the volume of water. So, yun nga, kasi zero air voids, ibig sabihin wala tayong, there is no air in the spaces. So, all spaces are filled with water. So, therefore, our degree of saturation is equal to 1. So, this is, we can now substitute. So, 2.67 times the moisture content, 0.14 times, this is equal to the void ratio E times 1. And void ratio E is equal to 0.3738. And now we can calculate the the maximum dry unit weight. So this is equal to 2.67 times so since we are in terms of pounds per cubic foot, this is 62.4 pounds per cubic foot times 1 plus 0.3738. And then we can get 121.2753 ECF. So this is the maximum dry unit weight of the soil at 0 air voids. So for the last example problem, an embankment for a highway 30 meters wide and 1.2 meters in compacted thickness is to be constructed from a sandy soil truck from a barrow pit. So the water content of the sandy soil in the barrow pit is 15% and its void ratio is 0.75. So the specifications require that the embankment to be compacted to a dry unit weight of 18.20 kilonewton per cubic meter. So the length of the embankment is 1.5 kilometers and assume that the specific gravity is equal to 2.70. So determine the volume of the barrow material required. So in this problem, we will simply have to write that the dry weight of the soil in the embankment is equal to the dry weight of the soil to be borrowed, or the dry weight of the soil in the the dry weight of the barrow. And then, and also, again, the unit weight is equal to the weight all over the volume. So, the left side is for the embankment or the required, and then the right side is for the barrow. So, the specified for the embankment. So, this is the dry unit weight times the volume of the embankment, and this is the unit weight or the dry unit weight from the barrow, and then times the volume no barrow. So we are looking for this one. So again, specified yung dry unit weight from the embankment. So this is 18.20 kilonewton per cubic meter times the volume of the embankment. So this is equal to 30 meters times 1.2 meter times 1,500 meters. And then for the volume, for the dry unit weight of the barrow, so this is equal to 2.70 times 9.81 and then this is, so the void ratio is 0.75. 1 point. So notice that we did not use the water content because we are dealing with dry unit weights. So times the times the volume in the barrel. So volume from the barrel is equal to 64,933.74 cubic meter. So that's it. We are already done with the 5th chapter. So see you guys in the next video. So we will be now moving to the vertical stresses. So that is the last topic in the soil mechanics, which involves calculations. And after the vertical stresses in soils, it's just all be some concepts so regarding the soil exploration, geosynthetics. So thank you class for watching this video, and God bless. See you all, and you can also subscribe to my channel and hit the notification bell so that you will be notified whenever I'll be uploading new videos. So bye.